Hi, in this video, I will discuss the relative importance of resonance structure and how do we determine which of the resonance structure that we have thus drew will be the most significant one. So not all resonance structure are equally stable. Thus, because we are able to draw them, it doesn't mean that they are significant or important. And the most significant one is the one where the molecule actually exists in predominantly at most of the time, and that's the one with the most stabilized electron. And here are the 4 rules how to determine which of the resonance structures that we drew would be the most significant or the most stable one. Rule number 1: octet and minimize formal charge. So the best resonance structure is the one where all atoms have an octet of electron and without any formal charge. Now, sometimes it is acceptable to have 2 or 1 formal charges, but structure with 3 or more formal charges should be avoided if possible. And again, the best one is the one without any formal charge at all. For an example, when we have draw the different resonance structure for acetic acid, these are the different resonance structure that we are able to draw right here. And now let's determine which of this would then be the best. So the best one is actually the first one. And the reason why is, in this case right here, all atoms have an octet of electron. And now all atoms have a 0 formal charge. So none of them have any charges on them. So that's why that this is the best one. The next one has 2 formal charges. An oxygen, this oxygen negative, and this carbon right here is positive. And this one right here is actually quite unstable right here. And in fact, we wouldn't even use the word okay, but this is actually unstable and not preferred. And the reason why is, if we ever have something that has a lot of electron, making it negative, right next to something that's positive, then this would then attract the electron to the point of charge, and we would have gone back to the other resonance structure already. So this is this would then be the best one. And this one right here also have 2 formal charges on them. This oxygen is negative and this oxygen is positive. And again, this is not preferred because we have 2 atoms carrying the formal charges. And rule number 2, if there has to be a formal charge, or basically if all of the resonance structure have formal charges on them, then the best one is the one where the negative charge locate on the more electronegative atom, and the positive charge should then locate on the less electronegative atom. Because electronegative atom prefer or likes or love electron, so therefore it's better for us to have the negative charge on them. For an example, let's say we have this molecule right here, and now we draw its resonance structure. One way we can draw resonance structure is, again, this nitrogen has 2 lone pair of electron, and we'll be able to draw the other resonance structure, and it will then be as follows. We'll be producing a double bond between this and the oxygen will now be negative. So when we compare between these 2 resonance structures right here, which one will be more stable, we will then see the following. The one on the left have the negative charge on nitrogen, and versus the one on the right have the negative charge on the oxygen. So between oxygen carrying the negative charge versus nitrogen carrying the negative charge, which one would be more stable with the negative charge? The answer, it would then be the oxygen, because oxygen is more electronegative. So that's the meaning to rule number 2. And now rule number 3, electronegative atoms such as nitrogen, oxygen, and chlorine can bear a positive charge on them, but only if they possess an octet of electron. So although this element right here, they do not want to become positive because they are electronegative, but now they can actually exist in resonance structure where they're positive. They won't be that very stable right there compared to all the resonance structure where this atom right here are neutral. But yes, they can be positive, but only if they can have an octet of electron on them. So for an example like this one, so in this case right here, these are the two resonance structure. Follow this arrow. This is what we will have. And then now between these two, which one will be more stable? The one on the left basically have the positive charge on the carbon, and the one on the right have a positive charge on the nitrogen. And between these two, which one is more stable? And the answer, it will be this one. And the reason why is because this one right here has all of the atom have an octet. So the carbon is basically not octet in here. Now having an octet of electron is really important. And in fact, that is basically one of the most important things that make resonance structure stable. Having all atom have an octet of electron. So in this case right here, on the resonance structure on the right, then all atom have an octet of electron, although we have a negative charge on the nitrogen. But then this would still be better than the other resonance structure where the carbon doesn't have an octet of electron. So this will then be more stable or more significant, because both carbon and nitrogen are octet, despite carrying the positive charge on the nitrogen. And rule number 4, avoid drawing resonance structure which two carbon atoms bear the opposite charge, especially when they're very close together. For an example, when we draw the orbital resonance structure possible for this molecule, we'll be able to draw this 3 resonance structure right here. And here in this case right here, we have a resonance structure in which one carbon is negative and one carbon is positive. So this one right here would not be a significant or stable one. And again, the reason why is because when this carbon right here is positive, it doesn't have an octet of electron. And now it is close by to a carbon that is very rich in electron. So this positive charge from this carbon will then attract this electron to come over and forming the double bond between these two carbons. And this is the reason why that this first one right here will then be the most significant or most stable one. This one right here, although that it's okay and it may exist, it is not as stable or significant compared to the first one, since this one has 2 formal charges on the resonance structure. And now let's try some of the example right here, how to draw this or of this resonance structure and identify the most significant resonant contributor. So this basically means the most stable resonance structure. So on the very first case of A, we can then see the following. So we can see that we have an analytic lone pair, and again this carbon right here, when this carbon negative, it means it has a lone pair of electron on it that we need to be able to recognize. So we have an analytic lone pair, and we can see that when we have an analytic lone pair, we can use that to form a double bond to the other double bond. And the resonance structure for this will then be the following. And now this oxygen right here will then become negative. So that's one resonance structure that we can draw. Now another one that we can also draw is the following. When going back to the very first one, before we do anything to this, that we can see that we have a double bond between 2 atoms of different electronegativity. So I can draw the arrow, so we can basically move the electron to the more electronegative atom and do as follow, and we'll be able to draw this resonance structure right here. And now this oxygen will become negative, and this will then be positive. But as you can see now, this one right here is not really stable, right? Okay, and so those are some of the resonance structure that we are able to draw. And now here we have a little lone pair, but if we were to do that, we'll go back to the initial structure. So these are the three resonance structure that are uniquely different. And of these three right here, which one would then be the most stable? The most stable would then be this one. The one where the oxygen is carrying the negative charge. Okay, so this would then be most significant and most stable. This is the major resonant contributor right here. And this would then be the least stable one. And please try the other example, and we'll go over this in class.